Welcome to the Passive House podcast, brought to you by Passive House Accelerator, a catalyst for zero carbon building. For news, inspiration, and connections from all flavours of Passive House, check out passivehouseaccelerator.com. Sign up to receive regular updates about events, get your questions answered, and contribute to the community dialogue. There's loads of free information for experienced professionals and people just starting out on their Passive House journey. We hope to see you at one of our weekly Passive House Accelerator live webinars. In the meantime, here's this week's Passive House podcast. Welcome back to the Passive House podcast. I'm Matthew Cutler-Welsh, coming to you from Auckland, New Zealand. And this week I'm joined by Zach Semke. How are you going, Zach?
I'm doing great. How are you?
Good. And we've got Mary James joining us this week. How are you doing, Mary?
I'm good. How are you?
Good. So I've still got the heaters on here in my part of the world, but it's been pretty warm over on your sides. Not the peak of temperature, but I understand there's a few fires blazing north of where you are, I think, Zach, at the moment. But is it pretty hot at the moment?
Yeah, it's warm, and it's not just that we have a lot of fires in Canada. Also, a whole bunch of wildfires in Oregon, some in Washington. So far, we've been spared by the wildfire smoke in Seattle, but it's definitely it 'tis the season. And then last week, I think both Monday and Tuesday were the hottest recorded temperatures for the planet in recorded history. So here we go. We need to figure out how to be resilient to this.
Yeah, not ideal. Which brings us to what we're doing today, which is the first in our series on cooling and resilience. So we're going to be running a special series of the Passive House podcast focusing on cooling and resilience throughout all of August and a couple of episodes into early September as well. Very topical, as you say, Zach. I've seen lots of reports of local records, but also global records of high mean temperatures as well. And this interview today that Mary has brought us, I think there's a couple of times in there that really highlight that change, where previous things that may have worked aren't really working anymore. People are having to start to switch strategies to keep cool and comfortable in their homes. So we'll get into that. But before we do, we've got some people to thank for supporting us.
We do. And before I jump into that, actually, I also want to say that for this cooling and resilience series, we want to hear from you all, the listeners. So if you have any DIY cooling or summer resilience solutions that you want to share or have to share, or have you come up with any fun solutions? Have you DIY'd or MacGyvered a ceiling fan or makeshift icebox or any other kind of device to help with cooling and also potentially with wildfire smoke? We'd love to hear that story from you. And so we'll have a link to an easy way to record a short message for us that we then will potentially feature on the last episode of this cooling and resilience series in a few weeks. So please check that out, and we'd really love to hear from you. We're getting some good responses, and I can't wait to get more. So I want to thank our stakeholder partner. Start with our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority, for all the support that NYSERDA gives to us in making our work possible. Thank you, too, to our founding sponsors, 475 High Performance Building Supply, Glavel, Ingui Architecture, Partel, Rockwell North America, Stocorp, and Zola Windows. Thank you, too, to our champion sponsors, Bewizo, Icon Windows and Doors, Intelligent Membranes, PH Air Seal, and Source 2050.
Great. All right. Mary, how did you come across our guest today? Have you worked with them in the past?
Yeah, I mean, Galen has, as he said, has been around in the Passive House community for quite some time. So I was excited to get him to come on. And Tad, of course, we used to work together, and I've known him for a long time. And I knew that a lot of different designs come across his desk and solutions. So I thought, yeah, good combination.
It definitely is a good combination, and a lot in this interview. So some great content in here. So let's jump straight into it.
Welcome to the Passive House Accelerator podcast, and we're doing a special mini series this summer on cooling and summer resiliency. So I'm here with two great guests to talk about this. The first is Galen Staengl, and the second is Tad Everhart. And I'm going to let both of you introduce yourselves. Galen, you want to go ahead?
Sure. Mary, I'm a mechanical engineer and started my work in the energy efficient green building sphere in 1999. At the time, I was working in California and was inspired by the work of Peter Rumsey out there, who was doing a lot of very high efficiency mechanical systems for different building types, and got hired by him and worked for him for a while, and then moved back to the East Coast and couldn't find anybody doing that level of design work. So started my own firm here in Virginia. And about 2008, I was introduced to Passive House by John Semmelhack, who is a local architecture grad here, and was building his own house and had studied the German system and was really excited about it. And that was sort of a turning point for our firm. We before that, I would say we designed really amazingly complex and energy efficient mechanical systems. And after that, we stepped back and started looking at the building more holistically and focused on trying to design simple, cost-effective systems to help shift costs to the building envelope. And that's sort of been our philosophy ever since.
Great. Well, welcome to the podcast. And Tad, could you please introduce yourself?
Sure. I'm Tad Everhart. I'm with CertiPHIers Cooperative. I'm living in Portland, Oregon, a very easy climate for cooling, and actually, frankly, very easy for heating too. I started on this path in 1998 when my first child was born, and I realized that even though I might avoid the worst of the climate crisis, she was going to live right through it, and got interested in solutions. In 2008, I attended the first organized Passive House training with CertiPHIers, and was active in Passive House Northwest and the formation of what later became the Passive House Network, and working with Mary on Passive House publications. In 2014, both doctors, Vita Feist and Wolfgang Feist, asked Albert Rooks and me to be building certifiers. And that was probably the highest and best way that I could contribute to the movement, because I'm neither an architect nor an engineer. It's kind of a closely guarded secret that I, in the past, was a lawyer. So I do know about rules, and I like to think that we don't just apply rules in certifying buildings, we actually help teams. So I'm thrilled to learn from Galen today and share what I've learned about mechanical heating and cooling in passive houses.
Great. So I want to start first with the situation of people probably more likely to be somewhere on the West Coast who have not needed air conditioning or mechanical cooling in the past, but summers are changing. We're living through yet another heat advisory day here. And, and they might be thinking, okay, well, what can I implement in the short term to just get me through this summer? So I want to talk about some of that. And I'm hoping maybe, Galen, you have some thoughts on, some of the classic passive cooling techniques are night cooling, but
Sure.
night
Yeah. Go ahead. Sorry.
only works in certain situations. I mean, so if you could talk about when night cooling is really advantageous and when it may not be so helpful.
So I will say that there's a group in Seattle that's been doing some work under a FEMA grant to look at basically emergency cooling techniques for folks in the Northwest and Northern California that don't have air conditioning when we experience these incredibly hot periods like the heat dome that sat over Seattle the last couple of summers. It can actually be pretty life-threatening for a lot of people that don't have air conditioning. So Michael Fowler with Methune and some other folks have been looking specifically at night cooling and how that can impact and improve, just keeping buildings cool enough for people to survive in these hot scenarios. And they found that, even during the heat dome, the nighttime temperatures did get down to, sort of tolerable temperatures, and that night cooling did actually bring the overall space temperature down enough to make it, much more manageable for folks during those hot periods. So, night cooling, the idea is you open the windows at night and you bring in as much of the cool outdoor air as you can. And in drier climates like the Northwest and Northern California, even when it's 95 degrees or higher during the day, the diurnal swing, that nighttime temperature drops 20, 25, 30, even more degrees at night, and makes it cool enough to basically charge the inside of the house like a battery and get all the surfaces cold, so that in the morning when folks get up and close the windows, it can keep that cool temperature throughout the day. And of course, in a well-insulated passive house type building, that's even more effective.
Right. Evaporative cooling is another, it's not passive, but it's another technique that works best in climates like that with low humidity. Have you worked with any evaporative cooling? I know there's sort of a fringe technique, but
yes, I have. There's a number of different approaches, kind of from the old swamp cooler, which is basically like a sponge where you would run water down and pull air through it, to other techniques. There's some folks that used to work with the Davis Energy Group that pioneered roof ponds as an approach, where they would build the house with a thin pond on top that might have insulation floating in the pond, and then a very, very small low energy pump would basically spray the water up on top of the insulation and let it run across the insulation at night. And there it would evaporate and cool through evaporation, and also radiate heat to the night sky and cool that mass of water on the roof of the building, which could then be piped into the building and used in fan coils for cooling. Or in some cases, they would just build the building so that the conductivity of the roof pond would cool off enough to cool the space below it. So there's a bunch of kind of wild techniques like that. But I think evaporative cooling, especially in dry climates, can be an excellent low energy way to get cooling, and also is something that can be looked at in emergency situations. I think that, those small, they also have something you can buy that's called can't remember the name of it. It basically makes tiny droplets of water, and you run that behind a fan, and you can cool the air temperature well below the dry bulb temperature just from the evaporation of the water. Tad, I'm wondering if you see any evaporative cooling in your work.
Well, we interfit our house in 2009, and we kind of hoped that we could get by on night flush cooling, and that worked until 2021, when we had 3 consecutive days, 104, 108, and 116. And I just have to say, by that second or third night, we were up at 78 degrees, sleeping almost stark naked with the ceiling fan all night. So night flush works. And what I like to mention to people is night flush requires you to work with your HRV. And like we usually just keep our HRV on the lowest level, level 1, with a Zender, not absent, but the lowest of the 1, 2, 3. But we found that if you're going to do night flush cooling, the HRV moves so little air through your house, you're really going to have to use your windows. But we also set our HRV up to level 2 for the hours of like 4 a.m. to 9 a.m. to at least try to move more air with the HRV. When we throw open our windows and doors at usually 6 a.m. is at the earliest that we'll get up, we'll also use box fans to try to get air moving, because unfortunately these hot nights are also stale nights. There's not a predictable breeze. Sometimes we have a predictable breeze, but in the worst heat domes we don't, because they're just kind of sitting over the city, and we live within 2 miles of downtown Portland, so we're in an urban heat island. But what we found is that the fans will help. We'll also switch our Zender to exhaust only, because with the windows open, if you extract air from the bathrooms and the kitchens, you can at least theoretically hold the heated air to the core of the house and push it out. Mainly, we've relied on prevention. So we do not have expensive mechanical blinds on our windows, east and west. We don't even have semi-expensive fabric shades. I just basically put up bubble foil. We take emergency space blankets, the kind that you use in survival mode. We use that with the foil facing out, hang that over our bigger east and west facing windows. It does help. We also grow vegetation over our west facing windows that is remarkably helpful. And on some of those hottest nights, we'll go out and water the garden at the same time we are cooling the house down with the flush, because if you can get the area around your house cooled down with that evaporation, that will help. But we also, some brain simple things that we do are, we don't cook on those hottest days indoors, pretty much not at all. We will maybe heat our coffee up, and it's a cold breakfast on those days. And it's also either taking our electric grill out into the attached garage. So it's kind of like the old cooking porches, right, throughout the Southeast, that people didn't cook indoors. That waste heat is really nice in winter, but it's awful in summer. It's bad enough that the refrigerator's kicking out heat into the kitchen. Sometimes during the days, especially if we've done a good night flush, we've gotten so much fresh air in the house, we'll turn our HRV down to absent mode, especially if there's few people in the house, because that reduces the communication with the really hot outdoor air. 2 years ago, we decided we better buy a window AC just to have kind of survival, other than going out and sitting in our Nissan Leaf and enjoying it air conditioner in the garage. And honestly, we've only installed it once, and it doesn't. It keeps one room really cool. But what I've noticed in a passive house is it's really hard to move air around the house. I was hopeful that if we cooled a room upstairs, that cold air would be like, a river rushing down our straight open staircase, and it hasn't happened. So if we have to rely on that more going forward, we're going to have to find a way to move that cooled air around our house. It just doesn't happen without effort.
And Tad, what about evaporative cooling? Do you see that, maybe not in your own home, but have you seen that in any of the projects that you've worked on?
I haven't. I know my colleague Christina Snyder talks about it. We have a weird evaporative cooler, and if you can indulge me a couple minutes, I'll describe it. And Galen can tell me whether I'm smoking dope or not. So we have a ASCO clothes drying closet, 2 foot square and about 6 feet tall. We hang a full load of damp clothes in that, and that air that gets pulled from the 70-degree house through that, and then the exhaust goes into the exhaust to our Zender, and the cabinet gets freezing cold to the touch. So there really is something to the cooling effect of the evaporation. I'm just not enough of a scientist to know if that is offsetting and to what degree the 34 watts that fan uses to pull the air through the cabinet. My sense is that it probably is reducing the mix of air extracted from the house at least a few degrees, but I can't prove it.
Yeah, that's pretty innovative. I haven't heard of that before, Ted. I like it.
I can send some pictures to you, Galen. I will say that just the case itself is, just heavy gauge steel, nicely painted white, and it is cold to the touch. I think it's because the air is moving through that cabinet, and all the clothes are hung up. So it's kind of like a ERV core. There's a lot of surface, and it's all evaporating.
Yeah, so the heat of evaporation of water is 1,000 BTUs per pound. So, how many pounds of water are you evaporating? 5 pounds? Maybe
Probably.
Getting 5,000 BTUs out of that load of wash. It's not bad.
Well, that's probably about right. That's probably what a wash is. I'm going to guess is that the damp weight is probably closer to, I'm thinking 7 to 10 pounds. The dry weight is considerably less. The nice thing is it runs usually about 5 hours to dry that load. So
yeah, and I guess the other part about it is what temperature is it when it comes out of the washer?
Oh, it's a cold wash.
Yeah.
Yeah.
So I too use the old-fashioned clothesline where I hang sheets outside my east-facing windows when it's really hot outside. But Galen, moving to East Coast, more humid climates, dehumidification is obviously one step that people can take to try and cool their house a little bit. Is that something that you ever talk about or would think
Absolutely. Yeah.
Solution?
Because of the humidity that we have in the mid-Atlantic region, and more so moving north as well with the changing climate, dehumidification is always a part of the conversation. And the interesting thing in residential construction, typically most of the humidity is coming in with the ventilation air. So we try when we can to remove that humidity from the ventilation air before it comes into the house or to the apartment building, as opposed to trying to take it out of the air after it's been mixed with the room air in the house. Because most of the indoor sources of humidity are relatively small unless you have very dense housing, or a lot of people in a house or an apartment. But sort of typical American occupancy, the cooking humidity and the showering humidity is not nearly as large as the humidity that can come in on a hot, humid day or a cool, humid day, 70-degree humid day here on the East Coast.
So those sort of room dehumidification equipment is not something that is going to make a huge difference to how someone feels in their
Oh, it does. Absolutely. Yeah. Making the air dryer definitely makes it feel more comfortable. The most of the small dehumidifiers are adding a fairly significant amount of heat as well back to the space because they dry the air out, but then that heat goes back into the space. So, the net maybe is a little bit of an improvement in comfort, but we're more concerned over here with the potential to create conditions for mold growth. So that's a big concern, especially in well insulated buildings that don't necessarily dry out to the outside by themselves.
And what about ceiling fans as humid climates? Does that help with making people feel more comfortable in summers?
It does, absolutely. That air movement definitely improves comfort. So we think it's a good idea in general to provide ceiling fans. And Tad, I've noticed the same thing. We live in a house built to Passive House standards, and it's amazing the sort of lack of air movement from thermal stratification in the house, and that makes me think that that a lot of the air movement from thermal stratification that we experience in sort of not very tight houses could be mainly driven by infiltration and stack effect from the house, right? So that you're leaking out up at the upstairs and you're pulling air in the downstairs. But it's amazing when you have a very tight house that the air does not stratify nearly as much as you would expect.
So, Galen, have you seen ceiling fans being used to distribute air better? Is that something that you've come across in your work in passive houses? Like as a strategy for dispersing heating and cooling?
Yeah, we've seen ceiling fans used to help distribute, like Tad was saying, sort of in a simple open house, the strategy of using a single ductless mini split really, in our experience, that works better if there's some mechanism like a ceiling fan to help move stuff around and distribute the cooler air.
Tad, were you going to chime in on that?
Well, I was just going to say that I agree with Galen that we're not getting any benefit from leakage to move the cool air around in our house. For instance, in the room that we've installed the window air conditioning, it has both a fresh air supply duct and an extract air duct. And I thought, well, if we run that air conditioner long enough, eventually it's going to cool down the house, because even though that extract air is only, I calculated, probably 1/10 of the whole houses extract air. Eventually, it's going to do the trick. It did not. And that room upstairs is right at the head of the stairs. The stairs are a straight shot down, 10-foot difference between the upstairs floor and the downstairs floor. And we have double doors, French doors in that room. So I thought, well, we're just going to have this cool cascade of cool air just, coming down that stairs like a river stream. No way. It just like was glued in that room. That you go into the room, even with the doors open, it was pleasantly cool, but it did not move to any other space. So I think that's the challenge. I read all these articles about people building passive houses in New England, and having the one mini split on the second floor, like at the top of the stairs, and that cool air would fall down. That's not what we experienced, and maybe it has to be literally in that landing area for it to work, or maybe you just run the air conditioning 24 hours a day and rely on the air movement. I'm kind of curious, Galen, what's your thought? You may have seen some of those articles that I read at the time too.
So we've worked on a couple of passive houses that have kind of taken that approach, and the most successful that we've seen are very open plan, sort of an open balcony on the second floor, open to below, so that there's just a lot of room for air movement. But even in those, I think a number of people have found that the bedrooms can get warm if they're not, sort of open to the space. And so there is some need for some fan to distribute things around. The original concept, right, coming out of Germany was that there was a limit to the heating load of about 3.2 BTUs per hour per square foot, and that allowed the heating energy required to be supplied through the ventilation air, which would be distributed to all the rooms in the space. And that's a little more difficult to do in cooling, because typically we supply cool air at 55 degrees, which is, only 20 degrees different from the room air temperature, versus heating we supply at 90 or 100 degrees, which can be, 30 or 35 or 40 degrees different than the room air temperature. So there's more energy in each cubic feet of air that's being distributed to the space. And I think there's some folks, Andrew Peel up in Canada is working on a system where they will actually deliver cooler air than 55 degrees, maybe 50 or 45 degrees, to get that delta T up and be able to deliver more cooling to the space through the ventilation air ductwork, which I think is a great innovative approach.
Yes, he's working on a study of that and how to optimize it so that there's not an issue with condensation. And we had him on the accelerator live, I think it was earlier in June. So
that makes a lot of sense, Galen. Thank you for explaining that. Our house, we do distribute the heat very successfully through the ventilation air, and we never, we don't really need to boost the ventilation air. Sometimes we will boost the ventilation air, which is kind of crazy, because then you reduce the efficiency of the air exchange with the outdoors. But just to pump it up quickly, you can, and we have a 2,500 watt induct, downstream of the core. but I never realized that the deltas are so different, and that's a great explanation on why that ventilation air is not sufficient to really distribute the cooling. So your temperatures were cool air is typically 55, and
Yeah.
and the warm air is typically what, 90 and to 100. Is that what you said?
Yeah, it can even be more than 100. And, there's a little bit of a challenge with most of the sort of traditional heat pumps that we have is they're pretty much designed to deliver 55-degree air. So it takes a little bit of a redesign of the equipment to make the air colder.
It's so Galen, for a homeowner who's like just now facing, I'm going to implement some sort of air conditioning system, and what have you seen recently that seems to you the most effective that you're seeing in the projects that you're working on?
So, our constant challenge is to find the most cost-effective solutions that deliver good comfort and good indoor air quality, so that we can keep the mechanical system costs low. And we don't do a whole bunch of single-family residential work. Most of the single-family residential work that we do, we end up with a ducted system like Tad was describing. And so we have two duct distribution systems, one for ventilation air and one for conditioning air. And we will, if we need to, have a dehumidifier, which is connected into the duct system. We strive to make those duct systems as simple as possible, because in a passive house, we don't have to, deliver air out at the perimeter of the building. We can just, sort of have one diffuser on an inside wall that's serving the entire residence. On the multifamily kind of apartment level, there's some exciting products that are starting to become available to the U.S. marketplace. There's a kind of a high efficiency PTAC, package terminal heat pump, that has an ERV in it and also allows you to connect an exhaust duct back to the bathroom. And that's IFOCA is making that, and it's supposed to be available, I think, early next year, which would be a very cost-effective approach for an apartment. And then there are some of these kind of all-in-one pieces of equipment that are starting to become available for the U.S. market, that have a heat pump and an ERV combined, and if put in a central location, can kind of distribute ventilation air and cooling with little or no ductwork to an apartment or a small house.
Well, that's exciting, both of those developments. That's great. How about you, Ted? Are there any innovative solutions that you're seeing in the projects that come across your desk?
We were for the first time seeing people getting away from wall unit and the ducted mini split units indoors to these, I don't know, Galen, what would you call them? Conventional central box indoor fan coils.
Sure, yeah, like a typical heat pump fan coil, like a ducted.
Yeah,
Yeah,
like I guess they're really whole house ducted systems, and those are running in parallel to the small diameter
right.
ventilation air, right?
Yeah.
So seeing those for the first time, as people really realize that their passive house takes care of quite a bit of the load, but definitely not all the load. I think especially in the harsher climates.
Yeah, and in a larger house, that's a nice, a nice aspect of that approach is that you can, not oversize the system because you're treating the whole house from one system instead of, putting a mini split in a different room or something like that.
Mm-hmm.
And it sounds like that might work well in a retrofit situation if somebody, had an existing forced air system but wanted to replace, their conventional furnace with a all electric.
Sure. Yeah. Yeah. One of the things that we're seeing with, the trend toward electrification is that it's really important to insulate a building if we're going to electrify it, because a lot of the older buildings, that might not have any insulation have really high heating loads and, a lot of infiltration through the building. And it's just very costly to serve that with a heat pump. But if we first, apply insulation and air sealing, then the heat pump is pretty small that we need to actually electrify the building.
Yeah, I'd like to say amen to that, Galen, because I realize that people only have so much money, but in the push for electrify everything, I've seen some heat pumps outside of single family homes. I didn't know that they were made that large. I mean, it almost looked like it was a heat pump that would be big enough for a passive house skyscraper.
Right.
And it's kind of like, yeah, it's electrical, but it's a huge electrical load. And it's just kind of sad because fabric first could have gotten them probably what we traditionally call a mini split, not, I guess, a maxi split.
Right. Yeah, exactly.
Absolutely. And this has been a great conversation. Before we go out, Tad, I thought you had one other interesting spot cooling that you wanted to talk about.
Well, sure. So we resisted ever getting refrigerant systems in our house just because we were passivista that thought that night flush cooling would do it all. And so it really was a hard call to buy that window AC, even though it's a nice little unit, probably doesn't leak as much as a mini split or multi-head system. But we really looked fondly at our sand and CO2 heat pump, because that's a refrigerant that can leak into the climate without really much global warming. And the damn thing's so quiet. We have it installed in our garage because we have a 2-car garage faces south. We just open the garage door and we have windows, operable windows in the garage. So there's always plenty of source air. And it's so quiet that I laughed that the only air conditioned part of our house was our garage, because when the sanding runs, it takes a lot of heat out of the air. And the thought occurred to me that maybe we could just put that inside the house someplace. We'd have to have dual water hookups and another electrical box. And the problem is it weighs 125 pounds. I'm not as strong as I used to be now that I'm arriving at senior citizen status. But it is remarkable that it is a silent cooler. And so I asked if anyone knew of a Sandin being installed deliberately indoors, and I heard of 2 situations. One being installed in the mechanical room where the equipment was to serve the elevator, because elevator equipment is on and it produces a lot of heat. But the other was in a hostel where there's a playroom and a weight room. So imagine a whole bunch of young people in there, either just having a great time or lifting weights or playing ping pong. And sure enough, I've a picture of the Sandin up there in the corner of the room. So that's, the classic twofer that we're always looking for.
Yeah, I love it.
Especially because after you get sweaty working out, you're going to need that hot water in your shower, right?
That's right.
Yeah, and just for people who don't know, a Sandin is a heat pump water heater.
Right. It is a wonderful heat pump water heater because it uses as environmentally benign refrigerant as anyone's been able to discover, and it's also remarkably efficient.
Yeah, it's kind of an interesting thing. We instead of using a heat pump hot water heater in the house, where we're getting the benefit of the cooling in the summertime and we're paying for it in the wintertime, that with the Sandin, we're putting the heat pump outside so that, we don't have that heating penalty in the wintertime, but we're not able to take advantage of the cooling in the summertime, so the ultimate device would be something that we could switch, right? So that we could take the cooling when we need it, and then we could, put it outside when we don't want to provide the extra heat.
Right. If Sandin would engineer a slightly smaller one that would perhaps have a longer runtime. John Miles tells me that for an average house, the Sandin, depending on source air temperature, is probably only running an hour or two, maybe per day. So it's not really practical unless it's installed indoors in a very big space, where it's just kind of be seen as a contributing factor instead of the sole. But I'm glad, Galen, that you raised the what I call the unitary heat pump water heaters, because those do seem like a really great solution with the twofer, at least in the summer and maybe in the shoulder seasons. And what we find in our customers in Canada, I ask them, you don't want to run that thing in winters. They say, oh, it's really easy. We just switch it to electric resistance in the winter. So that made a lot of sense.
Well, then you lose the COP, unfortunately.
Yeah.
Sure, but the first time we mentioned this to the Passive House Institute, they said, wait a second, you're using one heat pump to heat the space, and then you're using another heat pump to take heat out of the space. That makes no sense. It actually took them a long time to get their heads around that one.
Yeah.
But they don't live with, summer humidity and, like in New England and Mid-Atlantic and Southeast and Canada, Eastern Canada.
Yeah. So, for the last 30 years, I've been dreaming of a device, a system where, we could transfer heat from the refrigerator to the hot water heater to the heat pump, and back and forth. And instead of, just kind of treating them all independently and having them all do what they want and fight each other. But I don't know if we'll ever see such a system, but that's my engineering fantasy there.
Well, there's a great note to go out on. Are you listening, Mitsubishi? No. Thank you so much, Galen, and thank you so much, Tad, for coming and talking about how to get us through these summers. I really appreciate your time, both of you.
Thanks, Mary.
Thanks, Mary. Take care.
And that was Galen, Staengl, and Tad Everhart. Great chat, Mary. A lot in there. Obviously some really great experience. How would you kind of summarize your conversation?
Well, yes, I mean, that's exactly as you say, a lot of great experience. And we spent a lot of time talking about DIY solutions and really practical approaches to try and beat the summer heat. And also, unfortunately, how some of them aren't working as well as they used to. So we have to get a little more creative with our solutions. And unfortunately, in many cases, we have to rely on mechanical cooling when we didn't have to before.
Yeah. Yeah, I thought that was a really interesting point about that sort of tipping point of 2021 was mentioned of when night flushing was working, but there's a point at which that just hasn't been enough. And I guess it's also going to be different in different climate zones. And there were lots of different strategies talked about, from hot, dry areas to more humid areas, which I'm really interested in, having grown up in a hot, dry area and now living in a much more humid place where things like evaporative cooling just wouldn't work here in Auckland, but that it's very, very common in Adelaide in Australia, where you see these big boxes on top of roofs that are essentially straw bales that water trickles through, and it has a big fan just pumping fairly damp air into houses. And it's quite effective means of cooling without a refrigerant, but that just wouldn't work here in Auckland. Zach, what were your takeaways?
Well, one of them was the anecdote that we heard, speaking of the heat dome in Portland that Tad was talking about, and how they were, pre AC, he has that window unit that he talked about. But before then, getting up to 78 degrees at night, during the heat dome. I think there were two things. I mean, one is that clearly we're getting to a place where we do need active cooling in areas where that wasn't the case. That heat dome in the Pacific Northwest was completely off the charts. It's like it was totally insane that summer. So much hotter than it ever is otherwise. But the other piece was that is survivable, the temperatures he's discussing. So there's I think the combination of the need to be building better buildings so that we can be passively survivable, or that they can be passively survivable, and then also taking advantage of heat pump technology. So for both, and then at least we can do both heating and cooling with heat pumps. So there's a big advantage there.
Yeah, I thought that there's some really interesting reflections there from an engineering perspective about what a heat pump is doing, essentially moving heat from one place to another, which is advantageous if you're trying to heat a space. You're actually making another space colder. If you're heating water, then as a byproduct of that, you're creating cool air. Obviously, people have thought about that and tried to figure out, well, how can we make these things mutually beneficial for the overall benefit, plus situation. I don't know if that's easy to crack, but
yeah, no, totally. I thought that was like fun bookend with Galen's story, because Galen began the conversation about how he was moving to simplifying systems, because that's the beauty of the Passive House approach, is that you can take these big mechanical systems and turn them into smaller, simpler systems. But now that we have like all these heat pumps everywhere, there's this potential for sharing cool and warmth, and so there's that engineering brain of his is doing some dreaming, which would be great. I hope he cracks it.
Yeah. I think that initial comment is really important, though, about, and I always love it when I hear people who are trained in mechanical systems, mechanical service engineers, basically trying to sell less of the equipment that is their craft, and realizing that the smaller the systems are, the better the building is, because you've optimized the envelope first to reduce the size of that plant required. And that's relatively common practice now in larger commercial buildings, that being the focus. So I'm very interested in seeing that come down to the residential spaces as well, and saying, well, we could just chuck in a really big, as he called them, maxi splits. And I've seen some of the units that go in this part of the world. They got these two fans in the big double compressor units, multi-room systems, and they are huge. And there might be, I've seen some houses with 3 or 4 units like that along the backside of the house. And that just says, firstly, the house is too big, and secondly, it's too leaky. It's got too much inefficient glass, and you're asking it to work too hard. So optimize the envelope. But then we are also in the realm of trying to fix up a lot of existing buildings and working with what's there and dealing with those other strategies. I thought it was really interesting hearing about vegetation and what can be done outside of the building, reducing solar gain. I'd be really interested to get more into that as we go into this series on cooling resilience over the next few weeks. Anything else, Mary, to wrap up with?
Well, I thought it was interesting because it's not discussed that much about how in Passive House, and it was kind of fun that all 3 of us live in retrofitted passive houses, that the air doesn't move that much. And people don't talk about this generally, but that's certainly been my experience. And obviously also Tad and Galen to a certain extent have noticed that. And it's you have to work with that.
Yeah. So if you have an airtight house that doesn't, the stack effect doesn't really work, and because everything's kind of calm and still, and you don't have just big differences you don't have drafts, you don't have differences in surface temperatures around the place by design. So you do need to move things around. Also, there was the point about, it's kind of hard to move cooler air around than warmer air. And I think that touches on another really important aspect of this, particularly in the residential space, is that this is kind of specialist stuff. And when you're building a big commercial building, you get experts who are mechanical services engineers who have big brains and do flow dynamics and all sorts of complicated equations to design systems. And I think we will start to see more and more of that at residential scale, because you get some of these quite complicated issues of moving heat and moisture and also ventilation combined, and we need to figure that out for different size houses in different climate zones. And I don't think it's going to be one size fits all. And just another point, I think it's worth mentioning, when we talked about leakage, I believe that was referring to greenhouse gas emission leakage of refrigerants. And this is a whole nother issue, but that's something to be really conscious of when we're moving to more electrification, that some particular older style refrigeration units, some of the gases are pretty incredible gases, because they're just amazing at what they do to move heat from one place to another. But unfortunately, they're also really like off the chart level of greenhouse gas impact. So any leakage from those is a serious problem, and that's one of the advantages of some of these more modern systems, which are moving to refrigerants that have a much lower global warming potential. Ultimately, we want to get to, ironically, CO2 systems, which are way less of an impact than some of these other refrigerants. But my understanding, correct me if I'm wrong, Mary, but that was my understanding when they were talking about leakage in those systems.
Right. Yeah, they were. And it's also one of the motivations behind having point source heating and cooling system, and then figuring out ways to get the air moving that doesn't, that maybe uses a ceiling fan or jump ducts, as Tad was talking about.
Yeah.
It's, and not having longer refrigerant lines in the house.
Yeah. I learned from Skylar Swinford that you basically the expectation is that these systems are going to leak 5% of their coolant every year. So this is not like a theoretical, like maybe they'll leak. They absolutely leak. And so the volume of refrigerant is so important. So going back to that, insulating the house first, and then you can have a more cost effective heat pump system, because the heat pump is so much smaller. It also is a better, much better approach to decarbonization, because those refrigerants are so much less. I mean, over time, hopefully those refrigerants will get closer to CO2 level of global warming potential. But like Project Drawdown, that really excellent initiative to identify the key levers we have for decarbonization. One of the very, very top ones is refrigerants.
Yeah.
So
Yeah, well, it's kind of a clue when CO2 as a refrigerant is seen as
is the best.
As the best. Yeah.
Right.
That should be a signal as to how bad some of these other refrigerants are in terms of global warming potential.
Many orders of magnitude
worse than CO2. Yeah. All right. Awesome stuff. Well, that's a really great kickoff for our cooling and resilience series, Mary. So thank you very much for that. There's a lot more that we're looking forward to diving into. Zach,
and don't forget to share your story. Click on that link in the show notes so that you can share your story with us.
Yeah. So where do people go to do that?
It's a service called SpeakPipe, but you can just look for the link in show notes. Click on that and record a brief message for us explaining your DIY solution.
Yep. And if you're listening to this, you can just look up speakpipe.com /Passive House podcast. Love to hear from you. We've got a few messages already, which is really great. So use that to either ask a question or share a story about how you're keeping cool and making your house more resilient. We'd love to hear from you. All right. Well, thank you very much for listening in. Thanks, Mary and Zach. We'll be back again next week on Passive House Podcast.